Hi, my physics students. Welcome to another fun flip video with Mr. Bozadeh. Today we're going to be looking at projectile motion, and we're going to be applying our physics models to that projectile motion to predict where the ball is going to land. So I've got this launcher right here, and we are going to fire a ball on this launcher, like so, and we're going to be able to use our physics knowledge to predict where that ball lands. Pretty fast. In fact, I know that this model, the ball rolled back to me, of launcher fires the ball out at 4.8 meters per second. Now, what's unique about this setup today is that I've got that launcher set up perfectly horizontal. In physics here, we like to call this kind of a bomber projectile type problem. And we call it that because if you think about an airplane dropping an object, if the airplane's flying perfectly horizontal, then the object that it drops has that same horizontal velocity that the airplane had. And just like this ball, when it's fired out, has a horizontal velocity of 4.8 meters per second. So how do we solve problems like this? Well, we always start by drawing a diagram. So let's start there. Let's draw ourselves a diagram of this situation. There's the table, here's the ground, here's our launcher, and here's the ball flying through the air, projectiling down to the ground. As I said, the launcher is going to fire the ball out at 4.8 meters per second. So we know that that is the initial velocity of the ball when it leaves the launcher. And the other thing that I've measured previously with a meter stick is I know that it is 1.18 meters above the ground. After we've drawn a diagram, we want to put 0, 0, our origin in our setup or our picture. There's three places you might consider doing that. You might consider putting it up here where the ball's fired, down here where the ball lands, or right below the ball on the ground. That is going to be your best spot. Right below the ball on the ground is your best spot because if you put it there, then everything is acting in the positive direction. Everything's above there, positive in the y direction, everything's to the right of there, positive in the x direction. You can put it anywhere you want. That's just going to be kind of the easiest as far as positives and negatives go. After we've done that, the next thing that we want to do is we want to list our variables. Now, things get more interesting here because usually in the past we've just been listing our variables in the x direction for like a car driving or the y direction for something thrown straight up and down. But this is far more interesting because this ball is moving not only in the x direction, but it's moving in the y direction too. And one of the things that we talked about is that it's doing those things at the same time, right? But they're independent of each other. In other words, we talked about the fact that in the x direction, the mathematical and graphical model that it's going to follow is constant velocity. Whereas in the y direction, the mathematical and graphical model it's going to follow is constant acceleration. So in other words, however far it moves this way in the x direction, in the same amount of time move that far in the y direction. So it's doing both those things simultaneously. So it's doing those things independent of each other, but at the same time. And that's kind of a big idea. Simultaneous but independent. And so the motion in the x and the y direction are simultaneous but independent. So we're going to have to list our variables out in the x and the y direction at the same time, but independent of each other. So we've got our initial position, our final position, our initial velocity, our final velocity, our acceleration, our time. We've got the same stuff in the y direction. Our initial position, our final position, our initial velocity, our final velocity, our acceleration, and our time in both the x and the y direction. Now, two things that I'm going to change about this. So maybe if you didn't write that down yet, hold off on doing so. We're going to change a couple of things about this. The first thing we're going to change is the idea of time, because that is really the idea that it's simultaneous, right? Like I said, however far it moved in the x direction, it moved this much in the y direction at the same amount of time. So really, this time is not separate from the x and the y direction. It's not independent. That's the one thing that is not independent. The time is shared, or it's simultaneous. So when we write time, we just write time once because it's the same time in the x direction and the y direction to reach a point. Sorry, we got interrupted. So anyway, we've just determined that time was the same for both directions because it's simultaneous. The other thing I want to point out to you is that we are applying the model, and we talked about applying the model of constant velocity to this, to the x direction, but constant acceleration to the y direction. Since we're applying the model of constant velocity to the x direction, what I'm going to do is instead of writing v initial and v final separate, they're going to be constant. So whatever the initial velocity in the x direction, that's going to equal the final velocity in the x direction. So I'm going to try and write them that way this year to kind of show that they're the same. The other thing that we talked about is that because they're the same, the acceleration is 0 meters per second in the x direction. And in the y direction, really the object is just free falling, right? And so the acceleration in the y direction, as we discussed, is negative 9.8 meters per second. And so as this thing travels in the x direction at a constant velocity, gravity is accelerating it down at a rate of negative 9.8 meters per second every second. Awesome. So now we need to list our other variables that we know, the other values we can get from our word problem. Well, we know that the ball starts up at a height of 1.18 meters, so the initial position in the y direction is 1.18 meters. We know that the ball is going to land on the ground at a height of 0, so our final position is 0 meters. And we know that it starts in the x direction at a position of 0 because we put the origin right below it, so 0 meters in the x direction. Now there's two more values that we know, and this is a very important thing, and this is very specific and unique to the horizontal launcher or the bomber type problem. And here's what it is. We know that the initial velocity coming out of here is 4.8 meters per second. Well, that is entirely horizontal because it's a horizontal launcher. So that means all of that velocity is initially in the x direction. Now as it falls, it's going to pick up some velocity in the y direction, but initially all of it's in the x direction. So this is 4.8 meters per second, and it's going to continue at that speed in the x direction the whole time. In the y direction, it's 0 because none of this is pointed up, none of this is pointed down, so the initial velocity in the y direction is 0 meters per second. Like I said, as it flies through the air at a constant x velocity of 4.8 meters per second, it's going to speed up downwards because gravity is accelerating it. So we don't know what that final velocity is in the y direction right before it hits the ground. All right, let's talk a little bit about equations here real quick. In the y direction, we've got our full complement of equations because it's a constant acceleration. In the x direction, the only real equation that we're going to use is the equation for constant velocity. So in the x direction, our mathematical model says that position final equals position initial plus velocity times time. That's the only equation that we have there. In the y direction, we've got our final velocity equals initial velocity plus acceleration times time. We got our final velocity squared equals the initial velocity squared plus 2a final position minus initial position, like this. And we've got our position final, and I'm going to try to use the symbol y here. Position final equals initial position plus initial velocity times time plus 1/2 acceleration times time squared. So all we need to do now is pick the equation that lets us solve for time because we're going to use the y direction to solve for time, and then we'll use that to plug in over here. Since time is the shared variable, that is something you can expect to do when you're solving these kind of problems, projectile problems. You're usually going to solve for time in one direction and then use it to plug in the other direction. In this case, we'll start with the y direction, solve for time, and then we'll use time to find that x value. By the way, that x value, the farthest distance it reaches, we have a special name for that in the x direction, and we call that the range. So the range that is traveling in the x direction is that final x value. So it turns out that this one I wrote last is going to be the equation we're going to choose, and here's why. Because we have the final position in the y direction, we have the initial position in the y direction, we have the initial velocity in the y direction, 0, and that's going to make time go away, right? So 0 times time is 0. We have the acceleration in the y direction, so our only unknown is this t. So let's go ahead and plug in our values, and we see that 0 equals 1.18 meters plus 1/2 times negative 9.8 times time squared. So this is going to subtract the 1.18 over, so negative 1.18 equals 1/2 of negative 9.8 is negative 4.9 times t squared. Divide the negative 4.9 over, and so we get 1.18. I'll divide the negative signs out over 4.9 equals t squared. Square root this side, so the square root of 1.18 over 4.9 gives us a time of 0.49 seconds. So that ball is going to be in the air for 0.49 seconds as gravity pulls it to the ground. So gravity's pulling that ball down as it flies through the air, and finally after 0.49 seconds, boom, it's going to hit the ground. Well, now that we know that the time is 0.49 seconds, we can use that to find the final position in the x, or the range in the x. And we can use our constant velocity equation to find that. So we know that the initial position in the x direction is 0, so that's going to go away. So the final position in the x direction is going to equal the initial, or the constant velocity in the x direction, which is 4.8, times time, which we now know is 0.49 seconds. Multiply those two things together, and we get a final position in the x direction of 2.35 meters. So the range, 2.35 meters, is where that ball is going to land. There you have it, folks. So we were able to use our constant velocity model and our constant acceleration model and our equations and plug in our values and find where that ball is going to land. What I'll do now is I'll go ahead and we'll check it out, we'll test it out, we'll see how accurate we are. Right, here we go. So we've made our predictions. We predict that when we fire the ball out of the launcher when it's perfectly horizontal at a velocity of 4.8 meters per second, it's going to land 2.35 meters away. So I put one of our yellow calculator covers right there at 2.35 meters away. Let's fire it and see if it works. Ready? 1, 2, 3. Boom! Nailed it. There you go. So physics was able to accurately predict exactly where that ball was going to land, simply by measuring two things: the initial velocity of the launcher and the height of the launcher. There's a problem you need to do now for homework, the one right below this, so please do that for tomorrow. See you then.